All right. Yeah. So, many thanks to IAS and Professor Urvashi and Professor Vaipur for the invitation. And this talk is based on one of the recent experiments that my students did in the lab. This is on ultra-fast and ultra-sensitive charge amplifiers, which are basically electrical amplifiers. All right. Now, just to before we get in the meat of the talk, let me spend a few seconds introducing what are the activities that we do at ISER in our lab. So we have basically address two different kinds of systems. Both are two-dimensional. One is the van der Waals layered material system, and other one is the conventional two-dimensional electron gas based system. So in the conventional systems, we are interested in quantum sensing, especially quantum electrical sensing. And recently, we also have started working on. This is something which I had done for my PhD and postdoc. But now, after the Quest project, we also have started working on this quantum dot spin qubits. But that is what I am going to talk today. I'll talk some experiments based on mesoscopic electrical amplifiers. And we also work on two-dimensional superconducting circuits on van der Waals systems, and we recently also have a German project on spin valley states in these materials. Okay, so now the question here is, why do we need a charge amplifier? So what is the specialty of a charge amplifier? Okay, so the cartoon here shows the typical transport measurement, or maybe the most basic transport measurement that one would do, that is measuring the resistance of a resistor. So what you're doing is you are measuring the current as a function of voltage, or in some other case you measure the voltage as a function of current. But eventually what you're doing is you're measuring the number of electrons you have collected certain electrons or certain gauge per unit time. So, but there is a statistical nature to this transport of electrons. So if you say I have certain ampere or 10 milliampere of current, but that corresponds to some number n of electrons, some number of electrons collected at certain electrode per unit time. So, but because statistical nature, you can have at some point of time maybe delta t in one electron, maybe say 1000, the next instant could be 1002, the previous instant could be like 990, but there is a fluctuation in this number. And if the transport is uncorrelated, as I have shown here, what that means is it doesn't really matter. So what you always measure is the average number. That is what you do. Okay. But there is a distribution to it, and whenever the transport is correlated, then these higher moments of the transport are also very, very important, such as the skewness, kurtosis, variance, all these things. These carry very, very important information about the electron-electron correlation, interactions. There are effects such as bunching and anti-bunching of these electrons, short noise suppression, and all these details are there. All these things you measure current, all these things are actually, you are actually set under the carpet. That is what you do. So that is one aspect where measuring the charge as opposed to current can give you a lot more fundamental information than measuring the current. Okay, and there is also a few new technologies which depend on the charge measurement, or for charge measurements are very crucial for this technology, such as really high impedance systems. When the tunnel rate is very, very low, a most sensitive current preamplifier cannot measure anything better than like a 50 ampere. But I will show you at some point of time this talk, you can actually measure auto amperes or even lower current using these kind of charge amplifiers. I will show you at some point, one of the slides. And if you want to measure the state of a qubit, the qubit doesn't really run a current through it. You have an electron distribution. For example, you have singlet state and triplet state. Sorry for this typo here. This is a triplet state and a single state. So there is a slight distribution in the charge configuration, which you cannot measure by running current through the system. Of course, you cannot even run a current through the system because you are changing one electron with the other electron. Another electron in run a current through the system, then you are actually done. You lose the state. Okay, that is also another issue. Now, if you want to understand the correlated transport regions, such as fractional quantum Hall or Wigner crystal, you need to measure the charge the statistics of the charge, not the current. And last, but one of the most important aspects is the realization of quantum current standard, which are basically, which depends on counting the number of electrons and defining the current. That is the new art, which is, which is now, which a lot of research is going on in that field after the new definition of the SI units last year. Okay, so that is another aspect where you need a really, really sensitive current preamplifier, charge amplifier, where you can sense these electrons one by one. So, and this talk is basically about, realizing one of these really sensitive, at the same time really fast current, charge preamplifier. All right. So, just to, before we discuss the charge amplifier, let's look at the conventional charge amplifier. That is basically a field effect transistor, field effect device, electrical device, where the current through the source to drain is actually depending on the charge on the gate. That is the charge amplifier. So whatever the charge you apply, that gets amplified as a function of amplified in the control or transport system. So this kind of charge amplifier can sense only something like 0.1 electron per root hertz. That is the kind of the sensitivity you can have. And these are pretty slow, really slow, these devices. And these are also not suitable for various charge detection schemes because charge dynamics in solids happen at much faster time scale. And these are pretty slow. Okay, and these are also really large in geometry. So this is also not really easy to integrate with the modern quantum devices. So the charge sensor that I'm going to discuss is something slightly different. It's also another kind of field effect or field tunable device. So when I say field tunable device, let's look into what's the basic mechanism here. So these devices are basically realized on a two-dimensional electron gas system. In this specific case, it is a gallium arsenide, aluminum gallium arsenide system, where you have a thin quantum well, a two-dimensional electron system at the middle. And what you do is you deposit metallic gates on top of this crystal, on the surface of the crystal. And when you apply negative voltage, what you're going to get is you will get an image of that potential here. So in this specific case, when you apply negative voltage, you deplete the electrons underneath this gate and you make a small quantum well here. So this is an example how you make a gated quantum dot. And this is one of the debates that we have made recently. But what I'm going to discuss is a quantum point contact, not a quantum dot. So for that, what you need is you need two gates. So when you apply voltage on these two gates, you are going to deplete the electrons underneath and you make a thin channel here. That is called a quantum point contact. So if you look at the energetics in this case, you have the transport is confined by the quantum well in the Z direction. And in the Y direction, it is confined by the voltages here. So when you apply voltage on this gate, you are going to get something like a parabolic quantum well in the Y direction. And in the X direction, there is a saddle point, but still you can assume that electrons are free to move in the X direction. So the energy is basically n plus 1 by 2h bar omega 0. This comes from the parabolic well in the Y direction plus the energy in the X direction. And Z direction you don't need to consider because the electrons are not allowed to move in that direction. So you don't need to worry about that. So this is like a thin channel where electrons can propagate in one direction. And if you apply boundary conditions, what you can assume is something like a electron waveguide. So this is an image where the group has used a scanning probe tip to image the wave function or image the charge distribution through one of these channels. And you can see that there are well resolved integer number of channels, just similar to an electromagnetic waveguide. Okay. And this is a picture of one of the device, scanning electron micrograph of one of the devices that we have made recently. And if you apply gate voltage and measure the current, gate voltage means if you apply voltage on this gate and measure the current through the system, what you're going to see is you will get a step-like behavior in the conductance, and these steps are quantized at 2e square by h, that is the conductance, that is twice the conductance quantum. The 2 factor comes from the spin d geometry. If you apply a near field, all this will just go into e square by h in terms of the step size. And it's easy to understand this from something called lambda or Whittaker formalism, where each reflection mode through this channel is going to contribute e square by h to the conductivity. So that is where the quantization is coming from. So that is the 101 or physics, how you get quantized conductor through this channel. So what I'm interested is the really sharp region somewhere here between the last plateau or last step and the one where the current goes to 0. So here the transport is really sensitive to electrostatic environment or potential fluctuation in the vicinity. So if there is any small fluctuation, even due to an electron moving around, that is going to reflect in the change in the conductance of this device, the quantum point contact, the QPC. And so you can watch what is the change in the conductance of the QPC, or what is the change in the current, and you can calibrate that to the electron moving in the vicinity. So remember, now you are talking about an electron moving in solid in the vicinity. One electron you can detect with the spatial resolution and also temporal resolution, which is really a remarkable achievement. So here, this is a gate pattern of one of the quantum dots, where assume for time being that this is a trap for electron, and electrons are actually going through a system in random manner for time being. Okay, and what I'm doing now is I'm measuring the current through this channel. That is what is plotted here. So you can see that the current is going to give you something like a telegraphic signal, random telegraphic signal that correspond to an electron tunneling in and out of these tunnel barriers, which defines this quantum dot. That is captured by the QPC with a time resolution of like a few milliseconds. So in this experiment, these tunneling events are specifically slowed down for certain different purpose. But what I'm trying to say here is you can detect the motion of electrons in real time, in real space, in the circuit. If you calibrate the number of tunneling events, you can get that what we are measuring is something like a current in the range of auto ampere, 10 to the power minus 18 ampere. So whenever the current is high, what that means is the channel is feeling less negative charge, okay, or higher electric field. What that means is the electron is not inside the dot. Whenever the current is low, what that means is this channel is feeling more negative potential. What that means is the electron is inside. That is how you calibrate this signal. Okay, and in this specific case, what I have here is I'm looking at this signal and sweeping the level. You can see that this electron inside the dot is represented by this level here. Okay, and I'm sweeping this level across the Fermi level. And what you can see is whenever the level is low, electron level is low, most of the time the level in the QPC current, which is sensor current, is low. What that means, the electron is most of the time inside. But there are occasional ups. What that means is still it's a quantum state. There is a probability, finite probability for this electron to tunnel out. What that means, the current, there are occasional ups. But you can see as you move up the level, these in and out, these ups and downs are almost equal. What that means, the electron is, the electron has equal probability to be in and out. This is what it's represented. And when it is high up, you can see level is most of the time high, but there are occasional downs. What that means is, though this is a higher energy state, but still there is a finite probability for electrons to go here, sit here. Those correspond to these low states here. If we look at the occupation of the dot, that should be decided by the Fermi distribution here, and that is what I have plotted here. I just look at what is the occupation time of the electron inside dot by looking at this time signals here, and you can perfectly fit that to Fermi distribution, which is going to give you something like a temperature for the electron that is 220 millikelvin in this specific case. So the point here is you can measure the current through the system by measuring the charge one by one, and you can go down to even really, really low current levels, which are anyway, you cannot even dream that you can do this with any kind of current pre-amplifier. Okay, but the point is, this is a slow measurement. The time resolution is only 1 millisecond. So, but lot of charge dynamics in the solids, in solid state devices, much faster. So what we need a much faster current preamplifier. So that is aim. But the issue here is these devices are really high impedance devices, which are connected by meters and meters of wire. This is a representative diagram, wiring diagram. You just, for the time you know about all these all these blocks here, all these captions here. What I am trying to say here is you have meters and meters of wires connected from room temperature down to this device. So that is going to limit the bandwidth because you have high impedance device and you have a lot of capacitance coming from the measurement wires. So what I'm trying to say is that is going to give you an RC time constant which is only of a few milliseconds, and that's what we have seen in the previous slide. Okay. So, and then since you're operating at a lower frequency, 1/f noise is also an issue. So that is going to limit the signal noise ratio on top of all this. So our aim is how to push the operation of this device to a higher frequency so that you can detect much faster charge dynamics. So the first generation of this is something called radio frequency operation, where you have embedded these high impedance devices in a tank circuit. RD represents here the device which is the quantum point contact, and you have a LC tank circuit, lambda element tank circuit at resonance, which is given by omega 0 1 by square root of LC here. At resonance, what you have is you have the reflected signal from the tank circuit, that is VR, is a function of the device impedance. So it is L by CRD. This you can call the simple math. So the take-home message here is the reflected signal from the tank circuit at reference is a function of the device impedance. So whenever the device impedance changes, the reflected signal will change, but at time scale prescribed by the tank circuit. Now in this case, you are far away from the usual 1/f regime, and you can decide what frequency you want to measure it, but you have to choose the L, C, and RD appropriately so that you get a good reflected signal. That is the technology. And this is one of the devices that we had worked some time back. So here the inductor is a on-chip inductor which is lithographed, and the capacitance come from the capacitance of this connecting pads itself. So you don't need to add a specific separate capacitor. But that is also a downside because then a lot of this spare capacitance is going to play a determinant role to your Q value, or bandwidth, and all these things. So that is the downside of this technology. But the crux of, or the message here is the reflected signal is going to get modified or modulated by the change in the device impedance. So whatever the device impedance, that is going to change the device impedance, that is going to amplitude modulate the reflected signal from this tank circuit. That is the technology. Now, this is one of the first attempts where there is a quantum point contact, which is similar to the one which I have showed before, which is trying to detect the charge dynamics in this gated quantum dot. And this is a tank circuit. This is operating at around 230 megahertz. You can see that the reflectivity is depending upon the conductivity of the quantum point contact, GQPC here. And they were able to operate it at with a bandwidth of 10 megahertz. Okay. And they were able to acquire, usually this plot, which is shown here, takes an overnight to get any data. So here they were able to get 1 million data points in 180 seconds. That is 3 minutes of time. They were able to finish whatever they used to do in overnight scan. Okay. So that is how fast this can operate. So, but that is about acquiring data. But if you look at the operational frequency, it's only hundreds of megahertz, but the bandwidth is only 10 megahertz. And the control, how you control the Q value, how can you operate a higher frequency, and all these things are actually controlled by the lambda element nature, which is kind of uncontrollable quite often, because especially the spare capacitors, spare inductance are not easy to control. So you don't have a lot of knobs on controlling these things. So these devices are pretty good for this purpose, but still the not really fast to operate at a time scale where you can detect the charge dynamics in any given system at a fast time scale. So what we actually looked into is integrate this quantum point contact to a planar microwave cavity. Okay. So here this is a cartoon of a coplanar waveguide resonator where the resonance frequency is given by this formula where L is the length and the effective dielectric constant and C is the capacitance. Okay. So C is the velocity of light, and these are the field distribution. And this illustration shows there is the first. This is the first first mode, magnetic field mode, and electric field will be high at the end. Magnetic field will be high in the middle. So you have capacity gaps in the center conductor, which will work which will give you like a standing wave pattern. That is the resonator. And these structures are routinely used for coupling quantum state of superconducting qubit to the photonic modes. And these are in the superconducting qubit community. This is a well-matured technology. But recently, the semiconducting qubit community also has started looking into these devices for coupling the spin states into the photonic degrees of freedom. Okay. So now what we have done is we took this device and try to integrate with the quantum point contact and try to see how fast we can get information in and out of the quantum point contact. So we have a CPW resonator. Quantum CPW means Coplanar waveguide resonator of something like of this geometry, and this is simulation done by a high frequency simulation software, which will find out where are the resonances. And these are actual measured resonances, and this is simulated electric field distribution for the lambda by 2 resonance and lambda resonance, and this is magnetic field distribution. Okay, we are interested to operate with lambda resonance. Okay, I will tell you in a minute why we are interested in that. So the reason is you want to couple this quantum point contact galvanically to the center conductor. That is our aim. Galvanically means you want to apply DC bias to or run currents and apply bias to the center conductor. So if I operate at lambda resonance, there is a prescription where you can feed the current, DC current, the center conductor at the low impedance points, which are located at lambda by 4. Okay, distance from the ends through a lambda by 2 section of the waveguide. This is the format. Okay, so this is a resonator, and you can see these are the field lines in a meander way, and you are feeding this DC signal to center conductor through this inductor. Okay. Okay. So now the idea here is you measure the resonance, which is that first of all you measure the resonance modes of this waveguide, and we look at the resonance mode, the lambda resonance at around 3.4, and this since time is short, I think I got a message. I'll just go a little bit fast here. So what you do is you measure the reflected power at the reference as a function of the QPC impedance at various points. And you can see that the reflected power, the S11, is actually changing as a function of the operating point. But we can say the Q value is changing as a function of the operating point of the resonator. So I can apply a small AC signal here, which mimics a small charge signal, something like of order of 0.201 E squared by H. And I can see what I'm going to get the reflected signal. As I mentioned before, the reflected signal is going to be amplitude modulated by the signal, which is going to appear as sidebands in sidebands. And from the signal to noise ratio sideband, you can calculate what is sensitivity we are getting. We are getting something like 1.5 to the power minus 7 E squared by H, that corresponds to 12 picosiemens per root hertz. And that is at 10 megahertz. So now we will move on to demonstrate how fast we can operate this. So the bandwidth of this resonator is close to like 3 to 250, but the signal noise ratio we can measure as a function of the carrier frequency, and we can determine the bandwidth is close to 155 megahertz. And this is also demonstrating the same thing, where we have varied the frequency of the applied gate excitation, and we can detect a fairly nice, fairly good, signal noise ratio and a fairly good sensitivity up to 240 megahertz, which correspond to like 4 nanoseconds in time scale. And I can also say that the superconducting resonator is playing a major role in getting you really good signal noise ratio, because when I vary the temperature above 1.2 Kelvin, the aluminum superconductivity is actually killed, and you can see that the signal noise ratio has gone down. This is for base temperature, and this is for 4 Kelvin. So what I'm trying to say here is the superconducting resonator, whose Q value and the low loss nature is actually helping us to get a really high signal noise ratio and achieving a very fast detection. So this is about the other half, but I'm not going to go through this slide because it's about operating this device. But the message here is we were able to operate this with a short noise limited detection scheme. That is all I want to say. And the next step is basically going to the quantum limited detection. That is something which we are working on, but we believe we are pretty close to that. And I want to conclude by mentioning crediting the team who are behind this work. So Prasada is the leading person who did most of the work, and with the help of Anusha and Chitra. And many thanks Vipur and Rishi for the invitation, and thanks for listening.